Thank you. So, recall from yesterday that given a surface with marked points and a triangulation on it, we can associate some category, which is an abelian category, a module category. And so this was the first part of my last lecture. And secondly, we have seen that if we have a certain triangulated category which has some property like 2 Calabi-Yau property, and with cluster tilting object, then we have a nice notion of mutation. So today I will relate these two constructions, and somehow I will explain how it's possible to construct such a category, but somehow related with this. And finally, I will really, we also have given a triangulation. We have also the cluster algebra associated to it, and I will finally relate all these three things. Okay, so I will start with explain you what is a cluster category. So I won't define it very precisely, but yeah, it's just a motivation. So I will start with a very big theorem, and I won't put names yet on this theorem because there are too many names to put, but I will tell you some names later. So the theorem is as follows. So there exists, okay, so given, so we start with a triangulated surface, then there exists a triangulated 2 Calabi-Yau category C sigma tau, with a bijection that I will denote by T between arcs, so arcs of the surface, between the arcs of the surface and indecomposable rigid objects up to isomorphism. Okay, so this is the first thing. And and this bijection satisfies that if that for any two arcs, alpha and beta, alpha and beta are compatible, so just meaning that they don't intersect, if and only if there is no extension between T of alpha and T of beta. And okay, so this implies, well, not completely clearly, but that this bijection will induce another bijection that I still will denote by T between triangulation of the surface and cluster tilting objects up to isomorphism. And, well, it's just given by the direct sum. I mean, if you take the set of all arcs of a triangulation and you take the direct sum of this. And so here we have the notion of flip here. So, and if you flip your triangulation, so you remove one arc, you replace it by another one, it's just the same as removing the corresponding rigid object and replacing by another one, and you get exactly this Iyama-Yoshino mutation of cluster tilting object. So this is really the picture, and moreover, so I won't explain the construction of this category because this is quite complicated and you need some big derived categories, but you have the following property that for any triangulation tau prime, which there is an equivalence between so C sigma of T, this cluster category, and you mod out by T of tau prime, and this will be equivalent to Q of the category of representation of Q of tau prime. So just let me explain what this means. So this is so the object in this category. Yeah. So just let me explain. If you write something like this, so the objects are just the same. The objects of C minus all the summands of direct factors of this object. So somehow you just forget this object, and the morphism. If you have a morphism at factor through M or through some direct sum of M's, if you have such a factorization, then it becomes 0 in this category. So this is a... Yeah. Okay. Yeah, this is some kind of a... But yeah, so this result is very nice because somehow it tells you that, in fact, this category. So I mean, this category is triangulated, and this is a module category, so it's abelian. So they have very different structure, but nevertheless, so you have to think that this category is very close to be this one. You have almost the same objects. You just have to add a few more, but just like n. And almost the same morphism, I mean. you have also more morphism in this category, but not that much. And what is nice here is that it's true for any triangulation. So somehow this category contains all this, well, it's not contains because it's not an embedding of category, but somehow it contains all these categories. And somehow you could see that this would be like, I don't know, maybe an affine chart for some variety, something like this. So it would be an abelian. I mean, you take lots of abelian categories and you glue them together and you get a triangulated category. Well, this is not the way it is constructed, but at the end, this is what you get. So what is nice is that you get all these categories somehow inside this triangulated category. And yeah, and then, well, this is not, when you see this property, it's not so surprising that given two triangulation, there is an equivalence between these two categories. This is an equivalence of triangulated category. And well, the problem here is that this equivalence is not, well, you have many different equivalences, so there is not one canonical one, so you cannot somehow, you cannot just remove this and say, I have one cluster category which just depends on the surface. It's not that easy, but still you have this, which is nice. Okay, so this was a big result.
Question. In this case, you fix the points, right? The base points are fixed, or you allow...
The base point, you mean M?
Yes.
M is fixed and never move. Yeah.
So this is for triangulations with fixed M?
I mean, this is M here and M here. Yeah. Okay, so yeah, this is a big result. So now I should put some names, and I will probably forget some names, but okay. So the first part, like the existence of this triangulated category, it was done in my thesis, and it was based on work of Keller and also of Labardini. And then somehow using this result of Iyama Yoshino, somehow you get this maps T, but just in one direction. So like it's an injective map from the arcs to the rigid indecomposable object. And the fact that this map is a bijection, this is again due to this Bröstle and Jung theorem I mentioned yesterday. And again, I mean, this also, but it's clear from one that this also will be a bijection. This kind of equivalences are due to Buan, Marsh, and Heiten, and also by Caldero and Keller. So I should add Caldero. And the last point here, it's a result due to Keller and Young. And yeah, okay, I didn't put dates, but well, it's between 2006 and 2011. I don't know all this. I mean, it's not so important. And there have been other construction of cluster category and especially associated to an acyclic quiver. And this was due to Buan, Marsh, Reinecke, Reiten, and Todorov in 2006. So this was just the construction of a cluster category associated to an acyclic quiver. So it's not, well, you have some intersection with this construction, but it's not exactly the same. But this was the first paper was actually spoke about cluster categories. So, okay, and yeah. So as a corollary of this result, we get that there is a bijection between, indecomposable object of C sigma tau and the set of generalized arc and this set of free homotopy curve. Okay, sorry. Modulo some equivalence. Yeah, okay, so this is just a direct consequence of the point 3, right? And the theorem I said yesterday, that we know what are the indecomposable object of the category of representation of Q tau prime. And then we immediately get this, and this, you see that this is nice because somehow you have a bijection between objects that do not depend on tau. So somehow this category is much more symmetric than the other one. And moreover, this bijection T is really closely related with this. I mean, so if you take T of gamma, it will give you M tau of gamma as object in C over T of tau through this equivalence. I mean, the construction of these modules is closely related with this map T. So one other question we could ask is, what is so in a triangulated category you have a shift functor, and what is the shift functor in that case? So what would be the topological interpretation of this shift functor? And this shift functor can be interpreted as an element of the mapping class group of the surface, fixing globally the set of points. And so what is this element? It's just, okay, for each boundary component, you take a curve around this boundary component, and you can denote by sigma bi not the Dehn twist around this curve. So this would be a boundary component, but just a fractional Dehn twist. You just send this point on this on this one. Okay, so this would be fractional. I don't know if this is the right terminology, but then twist. And then, so this sigma, let sigma be the product of all these fractional then twist. And then we have that T of gamma shifted by 1 is isomorphic to T of sigma gamma. So this result is due to Bröstler again and Q. And I don't know. I'm not sure about the dates, maybe 2013. Okay, yeah, so maybe let's take an example. Okay, so just look at this example. So we start with an hexagon and my initial triangulation. For my initial triangulation, I will take this one. So tau 1, tau 2, tau 3. And you remember that the corresponding quiver is the following, without any relations. And then take these 4 curves. So okay. So I would put name. So this one is gamma, this is alpha, this is beta, and this is delta. And okay, so the first thing we can see is that if I look at T alpha shifted by 1, this object is just correspond to moving this using this fractional then twist. So what I get is T of tau 2. No, sorry, it's T of beta. I never know in which direction. It's T of beta. And what does this mean? It means that, so yeah, maybe alpha. Okay, alpha is this one. This one is alpha. And beta is the other diagonal. So then it means that you should have a triangle. So here you taking this isomorphism, you take this isomorphism and you can complete this into a triangle. And what will be the triangle? Since here you have an isomorphism, so think about a short exact sequence. If you have an isomorphism, the kernel or the co-kernel should be 0. So here you have 0, and here we have T of alpha. So we have such a triangle in the triangulated category, which is, well, not so interesting, but it means that we have an extension between these two objects. We have an extension between these two objects, and actually they cross. The corresponding arc have a crossing, so it just coincides with the theorem. But also using so here we have an extension between T of beta and T of alpha. And since we have such an extension, by using the Calabi-Yau property, it means that we have an extension in the other way. So this means that also this is not zero. And what will be the other triangle? The other triangle?
So why does it mean we have an extension? It looks like the extension is zero.
Yeah, but still, it's. I mean, it's not an extension that split because it's not.
So I mean, what is the?
Okay.
I mean, why do we say we have an extension? I remember extensions like A to B to C, and then we have a short exact sequence, and the B in the middle is the extension of B by A. But here you just have a zero. Just for sort of non-experts.
Yeah. But it just, I mean, an extension that split, it's really something like this. And so this will be zero in this space. I mean, this somehow will be the zero map, but this is not the zero map. So this is something non-zero in here. Well, even if the cone is zero.
Okay.
But so the other way around, it will be a more beautiful triangle, and this will be the following triangle. T of delta, T of gamma, T of alpha, and T of beta shifted by 1. And this one, it's T of tau 2, because then you still have to turn this into tau 2. And this triangle, let me show you what it becomes in the category of representations. So somehow if we apply this functor so applying the functor from C to C over T of tau, what do we get to this triangle? What do we get? We get this sequence and here, while applying this functor, this will become 0. So here we get 0. And, well, somehow in here you should have T alpha minus 1, and T alpha minus 1 is again T of T2. So here again, when you apply this functor, you will get 0 here. So you get a short exact sequence of this form. And so what is this short exact sequence in terms of representation? So remember, so here we take beta. So beta is this curve. So it intersects the angle between t tau and t3, tau 2 and tau 3, meaning that the corresponding module is just 0, C, C with identity here. This one, so here you take alpha here, alpha intersect tau 1, tau 2, so here what you get is C, C, 0. And these two representations, so one is crossing the 3 arcs, and the other one is crossing just tau 2, so what you get is C, 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 and 0, C, 0. And the direct sum of this, so I could write it C, C2, C, and here it's 1, 0, and here it's 1, 0, like this. And you can check that actually there is a short exact sequence in the module category using this, of the following form. So this is just to show you that all these triangles, in fact, can be interpreted into, not only short exact sequence, maybe longer exact sequence, but still you can see this as exact sequence of modules. Okay. Yeah, so now I will directly, so here somehow we have a category in which the combinatorics of the triangulation of the surface is encoded. But we don't have yet a direct link between the category and the cluster algebra. Okay, this for the moment is just a category in which you have all the combinatorics of flips inside. So now I will explain you that in fact you have more, and there is and you have more, and so my section here, so I will speak about cluster characters. And I will cite a theorem due to Calderó-Chapoton, 2006, and the marginal result is due to Palu, 2008. So it says that there exists a map that I will denote by x tau from the object of the cluster category into the Laurent polynomial. So here this is x1 up to xn, where n is the number of arcs in a triangulation. And this map satisfies first, if you take the direct sum of two modules and you apply this, what you get is the product of the two corresponding Laurent polynomial. If you apply this map to the initial cluster tilting object. So if you take T of tau I, what you get is just xi. And the third point is that if x1 c between m and n, okay, no, sorry, if the dimension of this is 1, then you have the following relation. You have the following relation where B and B prime are given. Okay, so since you have an extension between M and M, so it means that you have a triangle of the following form, and you call B the non-trivial extension. I mean, it's not. So the triangle is not unique, but somehow B is unique up to isomorphism if you have such a condition. And using this Calabi-Yau condition, you have another triangle. So and this cone will be the B prime in here. Okay, and then as a corollary, we immediately get that, yeah, because I didn't tell you yesterday, but when you mutate cluster tilting object, in fact, to get, so from Ti to get Ti star, which is a replacement of Ti, the mutation of the, so inside T somehow, as a summand of T, and then you just remove this and you want to replace it like this, then it implies that, in fact, x1 of Ti star will have dimension 1. So actually, to compute this replacement, you have an explicit way to construct it, just computing the cone of some triangle. So as a corollary, we immediately get that x tau of T of gamma will be just x tau of gamma, where x tau of gamma is a map given in my first lecture. And this holds for any arc on my surface. But here somehow we get more, because we get a value for each object in the category, not only for arcs. So, and actually what is, I mean, a very natural question that you could ask me is whether the image of this map is in the cluster algebra. And it's not, I mean, I didn't find the answer. I think that for most people it's clear that it should be. And, but, yeah, so this is somehow, I'm working with my collaborator to give a precise proof of this, but somehow most of people in the domain, they think that it should be true. So with Plamondon, so we should be able to prove that the image of x tau sits in this in the cluster algebra. And so it's a direct, I mean, so just before we have seen that we have a bijection between arcs and rigid, indecomposable rigid object. And on Tuesday, we have seen that we have a bijection between arcs and cluster variables. So of course, then we get a bijection between rigid indecomposable objects and cluster variables. But this map gives you directly the bijection. Okay, so this is and this map is in fact very explicit. It's not, the theorem is not just there exists a map. So there is an explicit formula. So I won't give you the general formula because then I wouldn't be able to explain the formula to you because it's a bit technical, but I will give you an easier formula.
Why this is not obvious, since you know what are the indecomposable objects and they are all generalized arcs?
Yes, but I mean, so we have seen that the cluster algebra is the image of small x tau. I mean, is generated by the image of x tau, the small x tau.
Yes.
But this is just for arcs. So this is not for general arcs, and this is not for even loops. I mean, some elements in the fundamental group. 3 up to. This is not. So, it's obvious that for any gamma being an arc, then So what is not clear is that if you take a generalized arc, you should end up in the cluster algebra. If you take an arc, it's clear that you end up. But if you take a generalized arc, it's not clear that.
But don't you know how to make the module for the generalized arc from the pieces?
Yes, we know.
So then you apply the formula and you, no?
No. No, it's not. And really, I mean, for generalized arc, it's not that difficult to see actually that it works. But then you have also to check that if you take some module of the form something like this, that this belongs to the cluster algebra, and this is not clear. This is not clear. This, well, I mean, if you think it's clear, maybe.
No.
I think it's not clear. I mean, I don't say it's a big result, but it's not trivial. Okay, so the formula is due to Calderon-Chapoton. So if Q tau does not have oriented cycle, then x tau of an object M is given by following formula. So I will explain you in a minute. So it's a complicated formula. No. J minus the sum of. Okay, so this is a very complicated formula. And you have a marginal formula which is due to Palu, which is even more complicated, but maybe it's already something to see. So what does this mean? So D. So where first f, what I denote by fm is the image of this object in the category rep q tau. So it's just when you see this object as a module. And d will be the dimension vector of this fm. And so when I write x bar to d bar, it's x1 to d1 up to xn to dn. So this is the denominator of the formula. And so what is this? So here, here we take it's a quiver Grassmannian. So you take all the, of fm. You take all module in rep q tau such that the dimension of this module is E, and that are submodules of fm. And this is an algebraic variety. And this, well, then you take the Euler characteristic. So, yeah, I wanted to give you an example, but yeah, maybe I will just make it smaller. So just take this quiver and take fm to be the following representation. Indecomposable representation 1 0 and 0 1, and so then you have to compute for each dimension vector, which is, so here d is just 1 2 dimension vector d, and then you have to compute for each e. So for instance, for e being 0 0, and then you have to compute this variety, but so it's clear that 0 0 there is only one sub-representation of this representation of dimension vector 0 0. So then you get the characteristic is 1. But for instance, so if you take e to be 1 0, then you can check that you don't have, a representation of this dimension vector is never a sub-representation of this, so then you get 0. And if you take, for instance, 0 1, then you want to understand the sub-representation of this, and then it's the same as just line in C2, so it's just a P1, then GRE of FM. In that case, it's just pi of C, and then the Euler characteristic is 2, and so on. And you continue with any. Okay, so in practice, so it's very nice formula because it works, and you don't have somehow to perform flips or mutation. It's a direct formula, so which is very nice, but the problem is that you have to compute this characteristic, and in general it's a very difficult question, and in particular it cannot help to say, for instance, for the positivity conjecture, it does not help because it's not clear at all whether this should be positive or not.
Are they always smooth?
Yes. Okay.
What is FM? Is it fixed module?
Yeah, it's a fixed module. So then here, what I wanted to compute is key tau of m.
Is there a formula? It depends uniquely on m. Given m, fm is determined.
Yes, yes. If m is indecomposable, because somehow if you take m to be something plus tau of t of tau 1, say, then when you apply f, so f of this will be f of m. So because you taking f is just modeled out by this object. But if you take an object, so somehow I take the only indecomposable object having this image. And then, yeah. Okay, so in the last 10 minutes or even less, I will just speak about applications very roughly. So application of this categorification, but as you see, there is no precise way to say there is a categorification. I couldn't give a precise definition of the categorification of a cluster algebra, but still, when we have, so somehow we have the categorical side and the algebra or combinatorics of flips side. And we have some relation between these two. And usually when you do categorification, it's more as a tool to better understand the combinatorial topological side. And so actually, there are some results that are purely cluster algebra results, but that where the proof is using this category. So there is, for instance, the theorem, due to Cerulli, Labardini, Keller, Labardini, and Plamondon from 2013, saying that cluster monomials, so I will tell you what cluster monomials are in a minute, are linearly independent. So what is a cluster monomial? So if you take x tau of t prime of 1 to the power of m1, x tau of t prime of n to the power of mn, where t prime 1, t prime n is a triangulation. And all the cluster monomial, it's just the family of all these monomials where tau prime is in any triangulation. So you take, for any triangulation, you take the monomial in these variables, and you take the union of that, and the union of that is a set of cluster monomials, so it's a very big family, and they are linearly independent. And usually, when people look at basis of cluster algebras, well, they want this to be part of the basis because somehow it's a set which is really symmetric with respect to the flip and everything. And so there are some other proof, but so they gave the first proof of this fact, and their proof is really using this cluster character formula. And but yeah, so there are also a few other results. But as I told you, for the positivity conjecture, I mean, which is now a theorem, it's not really useful because we have this bad Euler characteristic, which are very difficult to compute in general. But here the fact is that this category is somehow it's interesting in itself because it's very close to categories that are studied in representation theory. So somehow we have also can use this dictionary in the other direction and use the cluster combinatorics to deduce some result about representation theory and categories. And in particular, so all these results so we have this very nice theory called cluster tilting theory, and which is mainly based on works by Osamu Iyama, and which is a very, very nice theory. And so it's called cluster tilting because, cluster, maybe I don't have to tell you why, but this tilting word is coming from representation theory side, and tilting is strongly related to derived equivalence. So a tilting object in a triangulated category is an object that gives you a derived equivalence. So that gives you a way to see your triangulated category as a derived category. So this object have been studied since the 80s, and this is a very classical question in representation theory. And actually using all this machinery, that seeing that these tilting combinatorics are very close to cluster combinatorics, so this was a motivation for the work of this categorification. And actually we can deduce some result in representation theory. So just to mention a bit more precisely, I have a joint work with Opperman and with Kremland, where we find a new derived invariant for certain finite dimensional algebras. And these derived invariants are really, can be computed really using mutation and flips and so on. So I cannot give you some precise explanation, but it's just that using all these categories, we can answer to classical question in representation theory. So thank you very much. I would stop here.